Good afternoon. On behalf of Engineers Australia, I'm delighted to welcome you all to our Thought Leaders series, Decision Making for Safety in Contemporary Engineering. My name is Amanda and I'll be your host for today. Firstly, in keeping with our custom, Engineers Australia acknowledges the traditional owners of the land and recognises their continuing connection to land, waters and community. We pay our respects to them and their cultures, and to elders past, present and emerging. Before we get started, I'd like to acknowledge that today's webinar is being hosted with Engineers Australia's industry partner, Engineering Systems Management. ESM is an independent engineering consultancy that is passionate about engineered safety, providing tailored solutions to more than 50 customers throughout Australia since 2011. ESM offers services in engineering management, systems engineering, safety and design, and functional safety. The company also facilitates and delivers engineering studies, hazard and operability study, as well as control systems, safe design reviews, layer of protection analysis, functional safety work on control systems, and safety in design training. Today, we will hear from two speakers, followed by a live audience Q&A, and I encourage you to send questions through to our speakers via the YouTube chat box. I'd now like to give a warm welcome to our first speaker, Professor Nancy Leveson, who joins us from Massachusetts today. Nancy is a professor of aeronautics and astronautics at MIT. Nancy conducts research on all aspects of system safety, including modelling and analysis, design, operations management, and social aspects, and in the larger arena of systems engineering. Nancy has served on numerous national and international committees and accident investigations, including being an expert consultant for the Colombian Accident Investigation Board, the Presidential Commission on Deepwater Horizon, the Baker Panel on the Texas City refinery explosion, and a Navy committee investigating one of the V-22 Osprey accidents, as well as lesser-known accidents. Please welcome Professor Nancy Leveson.
So I'm going to talk today about a powerful new approach to safety engineering. First of all, let's define safety and make sure that, because my definition is broader than often is used. An accident or a mishap, I just define as a loss. Any undesired and unplanned event that results in some kind of loss. Now, that could include human life or injury, which normally it does, but often it doesn't include some of the other things. Usually it includes property damage. Often it doesn't include environmental pollution, mission loss, loss of protected information, negative business impact, any kind of loss. And you also notice that it doesn't say whether it's intentional or not, just says it's undesired and unplanned. So this actually includes cybersecurity. And you can do cybersecurity in the same way you do safety. So finally, safety is just defined as the absence of losses. So let's look at the problem first. The problem basically is that our current safety tools are all 50 to 75 years old. But technology has changed in the last 75 years extremely. And if you look at this timeline here, on the left, you see in the 1940s at the end, we have failure modes and effects analysis, FMEA created, which was really created after World War II for reliability of electrical components. And then in the 60s, there were a lot of new techniques created, fault tree analysis, HAZOP, event tree analysis. But all of these techniques, which are still used today, assume that accidents are caused by component failures. Now, that made sense at the time because that was true. But since that time, and starting about in the late 1970s, we started to introduce computer control in the systems. There were exponential increases in complexity. New technology was developed. There were changes in the roles that humans played in these systems. And all of a sudden, the world of engineering and the world of the types of systems we were dealing with changed extremely. But the old techniques still were there. There's one new technique, and I'll talk about it, that was created about 10 years ago, Stpa. And it does handle these things, but the old ones don't. So let's look at what the problem is. The problem is that traditional safety approaches don't work on today's system. They don't handle the complexity of systems today. They don't handle software very well. They don't handle the new rules for humans. They don't handle management systems. They don't look at the social systems. They usually start too late. You need a design first before you can analyze it. The problem is that you don't have enough detailed design until fairly late in your development process. And if you find problems then, you're not going to be able to go back and change and start all over again. So there's very little that can be done. And hardware, humans, and software are all treated separately usually, sometimes by totally different types of techniques. So the first thing you would think, well, we'll extend the old techniques. The problem is that the underlying assumptions that accidents are caused by failures doesn't fit today's systems, and I'll show you some examples. So I believe that we need a paradigm change, and that's what I'm going to talk about tonight is this type of paradigm change. So if we look here in the blue circle, the analysis is often how can the software contribute to the loss? The brown hardware design, the analysis, how can the hardware fail? And in the green circle, we look at the operator separately. How can the operator deviate from the intended or specified procedure? The problem is that there are all these unplanned and new interactions between these things in integrated systems. So it's easy to overlook the system problems by looking only at the individual components. We need to have some way to look at the integrated system as a whole. So let me show you some examples. These are real accidents. This was some Navy aircraft that were ferrying missiles from one location to another, and you see they carry them on their wings in the normal location. One pilot was executing a planned test because they said, why should you just sit there doing nothing? And they told him to aim at his friend in the aircraft in front and fire a dummy missile. Now, the problem was that nobody realized this was so-called smart software. And what it was designed to do was to substitute a different missile if the one that was commanded to be fired wasn't in a good position. And in this case, there was an antenna underneath the aircraft between the dummy missile and the target. So the software decided to fire a live missile located in a better position instead. Not at all what was expected. If you think about this, what failed here? The pilot did exactly what he was supposed to do. The software worked exactly the way it was designed to work and it was intended to work. But in the whole overall design process, something went wrong. Here's another example. This is an Airbus at Lufthansa plane, but this has actually been on same problem has occurred in lots of different aircraft. They were landing in Warsaw, and the software protects against activating the thrust reversers. That's how you slow up the aircraft. You turn the engines to go against the way that you're moving. And if that happens, if the thrust reversers come on when the aircraft is in the air, then that's very dangerous. You could stall and crash down and land. So there's protection in the software to prevent the pilots from doing this. Now, it turned out there was a whole bunch of rain. It was very wet on the runway, and there were the wheels hydroplaned, and there were other factors that made the software think that the plane hadn't landed. So the pilots couldn't activate the thrust reversers and stop the aircraft, even though it had landed, and it ran off the end of the runway into a small hill. Once again, pilots did the right thing. The software did exactly what it was designed to do, and the problem was in the overall design of the process and the design of the requirements for the software. Now, here's another accident involving thrust reversers. There's actually lots of these we found. We found this accident causal scenario where we were using Stpa, this new hazard analysis method, to analyze why a plane might not stop when landing, may not decelerate. And we found this case and we said, well, we wonder if this has ever happened. It seems a little strange. So we looked on the internet and we found lots of them. And in fact, in all kinds of aircraft. And the problem is that the techniques we use for analysis and the ways we certify aircraft today for safety can't catch this kind of problem. Now, this is another similar kind of thing, but with a little twist. This was a Tupolev, a Russian aircraft. It was making a soft landing in Moscow, and that means it may have runway contact a little later than usual. So to account for that, and there was also a crosswind, which meant the weight on wheel switches, which is one of the ways that the software knows that the plane is landed, didn't activate, and the thrust reverse system wouldn't deploy, which is what happened in Warsaw. But here there was a little different, because in this case, the pilots believed that the reverse thrusters would deploy. They always deploy. And they had limited runway space because, remember, they landed a little farther down the runway. So in order to stop faster, they engaged high engine power. Instead, since the thrust reversers did come on, it accelerated the plane and forwards and eventually collided with the highway embankment. In complex systems, human and technical considerations can't be isolated. In fact, the traditional view of operator error makes an assumption that operator error is the cause of most incidents and accidents, and I'm sure you've heard that. So to do something about it, we have to do something about the operator involved, fire them, retrain them or something, or do something about operators in general, marginalize them by putting in more automation, which makes them farther away from the system they're controlling, and therefore they have more problems doing control. Or we rigidify their work by creating more rules and procedures that they don't and can't follow. In this cartoon, fumbling for his recline button, Ted unwittingly instigates a disaster. The problem is that all human behavior is affected by the context in which it occurs. So human error is a symptom, it's not a cause. As I said, all behavior is affected by context, and the role of our operators and our systems is changing. They're supervising rather than directly controlling. They're teaming with automation to accomplish the goals, and we're designing systems essentially in which operator error is inevitable. And then we blame the accidents on the operators rather than the designers. To do something about human error, we have to look at the system in which people work. And in fact, the bottom line is that human error is a symptom of a system that needs to be redesigned. So I promised you a paradigm change. Here comes the paradigm change. On the left is the old paradigm. Basically, it says prevent failures or accidents. In other words, treat safety as a reliability problem. On the right is the new paradigm, which says we enforce constraints on behavior. Instead of just looking at failures and errors, we want to enforce constraints on what behaviors occur in the system. That means enforcing constraints on the behavior of the individual components, which includes failures and errors. So we can handle all the old things. We're just adding some new things, because we can also enforce constraints on the interactions among the components. And that, if you remember the two examples, that was really where the problems were occurring, in the interactions. And in this paradigm, this new paradigm, we treat safety as a control problem rather than a reliability problem. Now, this is a very broad view of control. Component failures, unsafe interactions can be controlled through design, redundancy, interlocks, fail-safe design, all those things we've always done, and we can add more. Or it could be controlled through process, various kinds of manufacturing, maintenance, operational processes, or through social controls, government or regulatory, culture, insurance, law, the courts, individual self-interest. The incentive structure is a very strong way to change human behavior. So, and then what we're going to do is enforce constraints. What do I mean by constraints? So here's some examples. Aircraft must maintain sufficient lift to remain airborne. Or the example we had, aircraft must be able to decelerate upon landing. Public health systems must prevent the exposure of the public to contaminated water, food products, and viruses. We're certainly learning more about that recently than any of us wanted to. Pressure in an offshore well must be controlled. The integrity of the hull must be maintained on a submarine. Toxic chemicals or radiation must not be released from the plant. Workers must not be exposed to workplace hazard. This will work on occupational and workplace safety, just as in very complex systems. These constraints represent the system level requirements on the socio-technical system. STAMP is just a new accident causality model. It's based on systems theory, not reliability theory. It defines accidents or losses as a dynamic control problem versus a failure problem. It applies to very complex systems. This has been used on some of the most complex systems that are being built today. One of the things that's being used on, for example, is the replacement of the U.S. Minuteman International Continental Ballistic Missile System. And it's worked like a charm. The old techniques, we wouldn't even try to apply them because they can't be used on anything that complex. This works on simpler systems too, but it also stretches to complex systems. It includes all the scenarios from the traditional hazard analysis method, all the failure events. It includes everything the old methods find, but it includes these new component interaction accidents. I gave you examples of those: software and system design errors, human operator errors, the entire socio-technical system, not just the technical part. So, how does this work? All right, well, we create, let me give you a very oversimplified example of how we treat safety as a control problem. We have here on the left in blue, on the top, a controller. It could be human, it could be automation, we could have both. Within the controller, there's a control algorithm. Well, if it's automation, if it's human, it's really a decision-making process. And it issues control actions via some kinds of actuators on the controlled process. It gets feedback about the state of the controlled process, and that feedback is used to update the process model. So in the Warsaw Accident with the A320, the software thought that the aircraft was not on the ground, so in the air, so it wouldn't allow the reverse thrusters to be started. That was basically an example of the process model was inconsistent with the real state of the world. And in fact, software and human-related accidents often do occur when the process model is incorrect. That is, it's inconsistent with the real state. This will capture software errors, human errors, flawed requirements, and all these things. It also includes social factors. So here, this is for example, in an automated vehicles, we may have some kind of government administration, may have regulators, accident investigations, standards organizations, manufacturers, maintenance, vehicle dealerships, and so on. At the bottom here, the vehicles. But we can look at this control structure, the social control structure too. But we can look inside the vehicle in more technical depth. And here's an example of a more technical model. Both of these models are fairly oversimplified, just so that otherwise they get too messy. And here I actually put in the process models. There's process models, of course, in the other example too. We have the safety driver, the automation interface, routing, planning, prediction, and so on. And we do the analysis on these models. So here's an example of how this would work and how this explains accidents. I'm going to use the Warsaw Accident as an example. The hazard was an inadequate aircraft deceleration after landing, right? And we have here a model of, we have the pilot at the top, and the pilot is controlling a software controller in the aircraft, and that's actually controlling the physical devices on the plane, including the reverse thrusters. So what happened? How does this explain the accident? Well, here we say feedback indicated that the plane had not landed. That's because of the hydroplaning and the other clues that the software uses, the weight on wheels, didn't hold in this case. So the software controller said the plane hasn't landed because didn't get feedback that it had landed. The pilot, his process model says the plane's landed. I know it's landed. I landed it and I can see it. It's on the runway. I can see out the window. So the pilot issues a command to turn on the reverse thrusters. The software says plane hasn't landed. Was told to ignore that command. And therefore, the accident occurs. Now, let's look at the Moscow, the example for Moscow. It's really the same thing because the same problem occurred with the software. We have these same things, but we're going to add the human in here to show how the human should be shown to be the causal factor in the accident. So it starts the normal way. Feedback indicated the plane had landed. Software says the plane hasn't landed. The pilot's process model says, well, the reverse thrusters are going to come in. In addition, it's a short runway. I need more power to stop. So I'm going to not only engage the reverse thrusters, but I'm also going to engage high engine power and send a command to the software controller to do this. Now, the software, as in the other example, ignores the reverse thrusters because the plane hasn't landed. But no one told it to ignore the engaged high engine power, and so it does that. So you can see, hopefully, in this example, the kind of how this kind of a model can explain how more complex accidents that involve interactions among the components work. So how do we do hazard analysis with this? Well, I haven't got time to teach you this. It actually doesn't take very long to learn. It's about 3 to 4 days doing examples and so on. But let me give you just an overall feeling for what happens. What we do is we look at the control actions. We build the model and we look at what control actions can be issued. And there are 4 types. This comes from systems theory and theoretical foundations. There's 4 types of unsafe control actions. Control action commands required for safety are not given. Unsafe ones are given. Potentially safe commands are given too early or too late, or control stops too soon. And so what we do in the analysis procedure, which I can't teach you, but what we do is have a step-by-step process for identifying potential unsafe control actions, identifying why they might be given or were given if we're doing a retroactive analysis of an accident, and then eliminate or mitigate those scenarios. That's exactly what the old techniques do. The standard hazard analysis techniques like fault trees and other things you may be familiar with, except that they only don't include all the kinds of scenarios that could occur. So they included a lot fewer types of scenarios. We also have to include the old thing. And the old one said if safe ones were provided, the controller if the controller does send a message to the engine for the reverse thrusters to come on, there may be some failure in the engine that causes the reverse thrusters not to come on. So we include those kinds of failures too. Stpa is an analysis language, a system theoretic process analysis. It can be used on these kinds of models to identify safety and security requirements and constraints, to identify the scenarios leading to the violation of those, and use the results then to design and redesign the system to be safer. We can find hazardous design flaws in addition to failures. We can include software, hardware, humans, organizational processes. It supports the entire life cycle. We don't have to have it designed to start with. So we can start this from concept development. We can design safety into the system from the very beginning. So we don't at the end find that we've got something unsafe and have to go back and make changes. It can be used also to support test and assurance, production manufacturing, anomaly or incident investigation during and various other kinds of operational things. And in fact, and so here just another shows some of the tools and how this all works. STAMP at the bottom here is just a causality model. It's not a tool, it's not a method. It's just a way of looking at how accidents are caused. But from this foundation, we can build new tools, including hazard analysis, Stpa, accident analysis. The tool is called CAS. Causal analysis using system theory. And that's for when you already have an accident and you're trying to find out why it occurred. We can do security analysis. As I said, we can do organizational cultural risk analysis. We can identify leading indicators. Often systems, when they're operated, start to migrate towards states of higher risk and eventually, as this migration continues, we have accidents. This can identify how to, using Stpa and using these, we can identify what leading indicators we should be checking for. It can also involve model-based system engineering. And if you take the tools, you can use those to support system engineering, risk management, organizational design, regulation, certification, and so on. So is the approach practical? Well, it has been or is being used in a really large variety of industries. I'm estimating in automobiles, I would say about at least 80, probably more closer to 90% of the companies use Stpa. Aircraft and spacecraft, there's extensive use, it's growing. Defense systems are using a lot because they're building really complex systems and, of course, lots of software in them. So UAVs, the Air Force, ground-based strategic deterrence, that's a replacement of the Minuteman missile system. It's being used on that. It's being used on the Army Future Vertical Lift. That's the development of new future helicopters and rotorcraft for the Army and so on. Being used and most of the uses are in these so far are in these systems, but there's lots of people using it in ships and marine, air traffic control, medical devices, hospital safety. I know in Australia, someone up in Queensland, the modern hospital system is using this for analyzing accidents and other kinds of safety problems in hospitals, chemical plants, oil and gas, nuclear and electric power, robotic manufacturing, workplace safety, and so on. This has gotten beyond me. I don't even know how many people are using it because so many people are now using it. But we have an annual STAMP workshop, and last few years we've had over 2,300 registrants from 85 countries of the world. Everywhere in the world is amazing to me. I had to go look some of them up in my atlas. There are a lot of new international standards, autos, aircraft, and defense. They're created or are in development. Oops. So it's being used, is what I'm saying there. But does it work? And there have now been hundreds of evaluations and comparison with the traditional approaches that are used now. We've done some of them Lots have been done. Hundreds of them have been done by industry. Some of them have been controlled scientific comparisons. Some of them have just been people in industry. They'll do a parallel project, one using Stpa and one using their standard tools, and they do a comparison that way. Virtually all of them show the Stpa is better. It identifies more critical requirements or design flaws. And what surprised me is I assumed because this is so much more powerful, it was going to be more expensive. I mean, that's sort of, isn't that a basic law of nature? And then we started getting these reports back and finding out that Stpa actually required orders of magnitude fewer resources than the traditional techniques. And you could say, well, why would that happen? It's finding more. But what it finds is the more important things. It doesn't find things that aren't important, that really are irrelevant to real safety. The return on investments and the information about that is just starting to come in, and companies are being very closed-mouthed about it. They talk to me, but they swear me to secrecy. Most of them say, well, this is our proprietary advantage and we don't want anyone else to know about it. But one large defense industry contractor has spoken out, although I'm not going to use their name, and they claim that they're seeing a 15 to 20% return on investment when using Stpa. That's on the entire contract, 15 to 20% less cost for the whole contract. They claim that they've saved 4 to 5. They're not using Stpa. They're using it on a lot of things, but not on everything. They claim that last couple of years, they've saved $5 billion. That's with a B, by using Stpa. And they compared it. They used a lot of data to compare it to their old techniques and how much it cost them. And they did some parallel things, experiments. So if you want more information, I assume that these slides will be available to people. There is a website that has lots of papers, presentations from conferences, tutorial slides, tutorial videos, and other things, examples. And there are 3 books that you can get free. The first is my book that I published in 2012, Engineering a Safer World, which was the first book on this new work. Then we also have a handbook up on the web on Stpa. In the middle there, we put it up in 2018. There have been more than 160,000 downloads in those 3 years. It's been translated into Japanese, Chinese, and Korean versions by engineers there. They just wrote us and said, we'd like to translate it. If we translate it, can we put it up on your website? And we say, sure. No idea what's correct, but it's up on the website. And we also have CAST handbook, which is how the learning from accidents. We didn't put a count on that one. It's newer, but it's been translated into Korean and Japanese versions. I don't know whether that's in Chinese yet or not. So that's the end of my presentation. And I assume there'll be time for questions.
Thank you, Nancy, for your input. I'd now like to welcome our second speaker, Mike Hurd. Mike is the founder of Engineering Systems Management. His 30 years' experience includes working with high-integrity systems such as nuclear plants, submarines, rail signaling and control, and electricity transmission and distribution networks. Mike is a leader in safety design and has developed processes, templates, and training to improve systems and processes in engineering organisations. In 2013, Mike founded the Engineers Australia Engineered Safety Group in South Australia. This committee brings together safety professionals to promote safety in the engineering life cycle. Please welcome Mike Hurd.
Hello and welcome to this webinar on safety decision-making in contemporary engineering. And during the webinar, I want to explore some of the Australian context for decision-making, both within and outside engineering and design organisations. So my name is Mike Hurd. I'm the founder and director of Engineering Systems Management in Adelaide, and we've been operating for over 10 years. And in that time, I've assisted many organisations to find solutions and implement systems and frameworks to improve safety outcomes for their engineering projects, including sometimes helping organisations to determine what is reasonably practicable to meet a health and safety duty. So today I'll be sharing some perspectives on safety decision-making in engineering that we've learned over the years, and emphasising the point that safety decision-making can and does occur at all levels of the organisation, and indeed begins outside the organisation. So key points that I'll be covering today: safety decision-making occurs at all levels within an organisation. Safety legislation provides the basis for safety decision-making, and the basis for decisions tends to flow down, and verification of decisions tends to flow upwards. So in contemporary engineering, decision-making is complex. Design aspects are connected and increasingly interconnected. We're making more system-related decisions in addition to component-related decisions. Even straightforward design changes nowadays have system elements to consider and lifecycle elements. For example, modifying the curbing along a street, you have to consider things such as pedestrian behaviours, vehicle behaviours, cyclists, e-cyclists, scooters, skateboards, people with guide dogs, maintenance access, drainage, lighting, and signage. So it could be viewed both as a systems design decision and a human factors design decision, as well as a straight design decision. Now, work health and safety and in Victoria, the OHS legislation require that designs are demonstrably safe so far as is reasonably practicable. Now, in previous years, safe outcomes were commonly achieved with prescriptive design standards, sticking to a proven design and in some cases limiting innovation. Nowadays, a lot of standards have moved to a performance-based approach, not prescribing what you must do, but setting a standard that must be achieved. Now, an example of this, to prevent a fall from heights injury, the 2008 Code of Practice for the Prevention of Falls in Housing Construction used to specify that fall protection was required at heights above 2 metres. But the more recent 2018 Codes of Practice, managing the risk of falls at workplaces, there is instead the requirement to minimise the risk of fall by a person from one level to another. So we need to consider protection against falls from heights of less than 2 metres to be sure to comply. And what this has done is it's pushed the responsibility for decision-making down from outside the organisation to within the organisation. So who are the decision makers? Now, the decision makers are anyone making a decision for incorporation into a design that may affect the health and safety of persons who construct, use, or carry out other activities in relation to the design. So these could be technical people, designers and engineers, financial people who are making decisions about finances and project budgets, schedule people who are making decisions about schedule that affect design activities, and outside of the organisation, people setting the standards and codes and the benchmarks of what indeed is safe. So here's an illustration of what I'm talking about. At level 0, above the organisation, governments and regulators set the basis for safety decision-making and people who write standards, that sort of thing. Then at level 1, at the organisation level, we need to provide industry context and decision-making framework, which is still a set of decisions in itself. Then at level 2, at the project or asset level, we're providing the context and design requirements for project decisions and asset decisions. And then at level 3, there's the designers and engineers who are doing detailed safety management and decision making. So safety decision making requires a commitment at all levels, and safety decision making begins with the safety legislation, which reflects the desire of society for decisions to be safe so far as is reasonably practicable. It is the duty of the organisation to exercise due diligence and establish and use processes and frameworks for the planning, resourcing and execution of safety in design on projects. And designers are responsible to learn and follow the processes put in place by the organisation. So there should typically be a minimum set of safe design process steps to demonstrate that designs are indeed safe so far as is reasonably practicable. Now, each level has verification, a feedback mechanism to monitor and improve performance. So this diagram provides another overview of my thinking. It is an illustration of how the basis of requirements for safety decision-making cascade down through the levels as shown on the left-hand side of the diagram, beginning with the creation of laws by government above the organisation, the integration of those legal requirements into the organisation's management system, the application of the management system to a particular project or asset, and the requirements of the project into a specific system being designed by the designer or engineer, with the output being a design that is demonstrably safe so far as is reasonably practicable. Now, the right-hand side of the diagram illustrates how the decisions of each level are verified by the level above, with the designer's design being subject to verification and review within a project, and the compliance of the project to the organisation's processes being subject to verification and audit by the organisation itself. And the organisation is in turn accountable to governments and regulators through the legal system. So let's talk about level 0, above the organisation. So as I said, safety decision-making begins with the safety legislation, which reflects the desire of society for designs to be safe so far as is reasonably practicable. And some of the regulatory authorities who set the standards for engineering design processes can get into detail that affects all levels of decision-making. So at level 0, in the Work Health and Safety Act, section 22, brackets 2, we've got a fundamental duty of designers. The designer must ensure, so far as is reasonably practicable, that the plant, substance or structure is designed to be without risks, so no risks permitted, to the health and safety of persons. In Victoria, the wording is slightly different and the legislative references are slightly different in sections 27 and 28 of the OHS Act. A person who designs plant, a building or structure must ensure, so far as is reasonably practicable, that it is designed to be safe and without risk to the health of persons. So what we can see is that the legislation is fairly clear and consistent across Australia. And the WHS legislation applies to Commonwealth legislation as well. And note how the legislation discusses the safety of persons as opposed to the safety of employees or workers. So we really need to be thinking about the safety of all persons affected by design, not only workers and employees. Let's now look at level 1, the organisation level. So the organisation is the company or body corporate or PCBU, person conducting a business or undertaking. And for a design organisation, it is the company or PCBU's duty to ensure that designs are safe so far as is reasonably practicable. This means an organisation is responsible first and foremost, and it is the duty of the organisation's senior management, which might include officers under the legislation, to exercise due diligence and ensure the organisation meets its duties. So while individual design decisions relating to safety are made by designers, engineers, architects, etc., the responsibility for them doing so is structured and in a consistent manner that is the responsibility of the organisation. So here's a busy slide that I'm going to talk through. The contemporary engineering organisation meets its legal duty by including safety in its engineering management system. Now, this diagram shows some of the typical elements used by an organisation to create a framework for making effective safety decisions. Now, these could be individual standalone documents or integrated into other engineering management documentation. Now, starting at the top, We want to see a safe design or safety and design policy that provides acknowledgement of the organisation's legal duty and an overarching commitment for ensuring that its designs are safe so far as is reasonably practicable, and that design decisions are safe as well. A safe design or safety and design procedure then provides the detailed step-by-step instructions on how safety should be addressed through the engineering and design lifecycle. I've got an example of this on the next slide of what that can look like. The procedure sets the expectations and milestones of what should be done at each stage of the design for safety. Having a safety and design procedure allows the organisation to ensure that safety is addressed in an effective and consistent way across all projects in the organisation. And so it is not left up to individuals to make decisions about how decisions should be made. To support a consistent approach to safety, a safety and design procedure is often supported by templates and guidance documents which give a consistent output for safety activities within the life cycle. Now, the application guidance, which may be integrated into the safe design procedure, provides the legal context and detailed guidance on the organisation's interpretation and criteria for determining what is reasonably practicable to maximise the likelihood that decision-making is consistent across the organisation. That is, the law provides sufficient definitions of what is reasonably practicable in ensuring health and safety, and the organisation should in turn interpret this in the context of the industry and provide guidance on how reasonably practicable safety decisions are made, ensuring that the organisation fulfills its legal duty and provides consistency of outcomes. Organisations will commonly have contract clauses specific to safety to ensure that any consultants, design consultants or design and construct contractors also meet the obligations of the client organisation. And the third branch relates to having design authority structure. What I mean by that is a structure for the organisation to ensure that design and safety decisions are made by experienced and competent personnel within the organisation, and possibly outside of it in some cases. This typically includes an escalation path for escalating safety-related decisions when necessary to the right level of authority to arbitrate on decisions about what is reasonably practicable. The design authority structure is complemented by competency management, which can include safety and design training materials and competency records. Finally, an organisation will typically have some form of verification or auditing function as a means of providing feedback to the organisation that the safe design processes and procedures are being followed and effective, and that is often part of a company's quality management system. Now, in terms of a safety in design procedure, processes in the safety and design procedure should align with the organisation's engineering lifecycle, and typical safety activities would include seeking and recording lessons learned from the past, safety and design planning, hazard identification workshops and studies and exercises, safety report to disclose that the design is safe so far as is reasonably practicable and why that's the case, design verification, and as constructed validation. Now, don't worry that you can't read a lot of the information on this diagram. It is simply to show an example of how safety activities can be integrated into a conventional engineering process. So this diagram shows two swim lanes. The upper swim lane is an end-to-end, a cradle-to-grave design and engineering management process, which goes through the initial trigger for design work to be done, then concept design, then preliminary design, then specification for detailed design, the stages of detailed design, then issued for construction, design, commissioning, construction and commissioning, handover, operation and maintenance, and final disposal or reuse of the asset. And the lower swim lane maps out the steps of safety in design that can be done to demonstrate why and how the design is safe so far as is reasonably practicable. And this is the sort of process flow map that we're seeing in contemporary organizations. Let's now talk about the level 2 at the project and asset level. So project and asset managers apply the organization's processes within the context of the project or the asset. They determine budgets, resources and schedules for safety activities and decision making, and define the project and asset requirements in relation to safety, thus demonstrating how they're complying with the organisation's requirements. Now, planning. A key step in establishing a safety and design plan is to allocate resources and schedules for safety decision making. A key step is to establish a safety and design plan to allocate resources and schedules for safety decision making commensurate with the scope, scale and complexity of the project or design work at hand. There are typically 6 elements to look for in a safety and design plan or safe design plan. Firstly, an impact analysis, an analysis of the impact that the design will have on safety, and therefore a list of things to do for safety during the engineering and design lifecycle. Second, a consultation plan, recognising the legal obligation to consult between organisations and with stakeholders to make sure that the right consultation occurs at the right time to inform the design. Third, an information transfer plan, information transfer being one of the key principles of safe design, to demonstrate what information needs to be transferred by whom to whom throughout the engineering life cycle to make sure that end users and stakeholders understand hazards and understand how to keep themselves safe around the hazards. Fourth, as I mentioned, the safety and design escalation path for decision making or reference to it. And 5 and 6 are verification plan, validation plan, and design change control plan or management of change plan. And I wouldn't expect a safety and design plan to include the full verification, validation, and design change control plan, but certainly reference to them. So that we know how they're going to be managed. And that's on the basis that the absence of verification, validation, and design change control is demonstrably very bad for safety. Now, at the level 3, then, the designer and engineers sitting kind of at the bottom of the decision-making tree, but often making the key decisions to demonstrate that something is indeed safe so far as is reasonably practicable. So the designer will act in accordance with the organisation's procedure and follow 4 key steps associated with the design. First, identify hazards in consultation with end users and stakeholders. Second, for each hazard, apply the hierarchy of controls to identify hazard controls. Third, determine and then implement what is reasonably practicable. And fourth, maintain records including a hazard register and a safety report. So I've mentioned what is reasonably practicable numerous times. So what is reasonably practicable? I'm sure many of you know this, but the meaning and criteria of what is reasonably practicable are defined in legislation. And the designer should be directed by the organisation how to apply the criteria for what is reasonably practicable in the context of the organisation's industry and project and asset types. So reasonably practicable, this is the WHS Work Health and Safety definition. The Victorian OHS definition is very similar. So reasonably practicable means that which is reasonably able to be done in relation to ensuring health and safety, taking into account and weighing up all relevant matters. So there we go. We have to take into account and weigh up all relevant matters. We can't miss any. But we have to include A, the likelihood of the hazard becoming harm, B, the degree of harm that might result if the hazard becomes harm, C, what the person concerned knows or ought reasonably to know about the hazard or the risk and ways of eliminating the hazard or minimizing the associated risk, D, the availability and suitability of ways to eliminate the hazard or minimize the associated risk, and E, the cost associated with the available ways of eliminating the hazard or minimizing the risk, including whether the cost is grossly disproportionate to the risk. So in order to determine whether a hazard control and identified control is reasonably practicable, we can use this sort of flowchart to help us comply with legislation. And this is the sort of reasoning that designers and engineers will follow. So for an identified hazard control, the first question is it mandated anyway by a standard or a code of practice or the law? And if it is, it's reasonably practicable. It doesn't matter what it costs. If it's not mandated, the next question is the identified control available? If it's not available, it's not reasonably practicable. If it is available, the next question is it suitable for our situation and our application? If it's not suitable, it's not reasonably practicable. If it is suitable, the final question is the cost of the hazard control grossly disproportionate to the safety benefit? And if it is, it's not reasonably practicable. And if it's not, it is reasonably practicable. So in terms of determining whether a hazard control is reasonably practicable, we can use a graph such as this one, and we've got a plot on the x-axis of the whole of life cost of our hazard control, and on the y-axis the safety benefit. It's deliberately not calibrated because the calibration depends very much on across industries and organizations. But we can follow the logic that something that is low cost and has a high safety benefit is reasonably practicable. So we're just going to do it, just do it. Something that's low cost and has some safety benefit, we probably still need to do, just do it. It's reasonably practicable because the law says we should do what's reasonably practicable. And if it's low cost, it probably is. But for high cost hazard controls that have low safety benefit, it's probably not reasonably practicable. The control is probably grossly disproportionate to the safety benefit, and that can be calculated. But certainly where you need your calculation to support these decisions is when you've got high whole of life cost hazard controls and that have a high safety benefit, and that's usually where you need some analysis to determine whether something is indeed reasonably practicable or grossly disproportionate. So in summary, safety decision making is made at all levels, and it starts above and outside of an organization. And at every level, decisions should be safe so far as is reasonably practicable to comply with safety legislation. And while safety decision making is often pushed down to designers and engineers, the decisions they make should be in the context of and verifiable against the organization's criteria for decision making, and thus the legal framework within which the criteria sit. Thank you very much for listening to the webinar, and that is where I shall finish. Thank you.
Thank you. A huge thank you to Nancy and Mike for their presentations this afternoon, and a really big thank you to Nancy. It's now very late at night in Boston, and she's agreed to hang around to take your questions. So I do encourage you to send questions through. You can do that by posting them in the YouTube chat box, and if you could say who your question is for, that would help us out enormously. We did get some questions from people who put them through when they were registering for this webinar, so we might start there. And I'd like to start with you, Mike. And we've had a question that's come in from Reese, and Reese is based in Queensland. Good afternoon to you. Reese is asking, can you talk about the safety and design process and the necessary legislation that's required to be followed, and how to ensure that we follow it? Mike.
Yes, thanks for that question, Reese. I think the safety and design process broadly follows 4 steps, and the first step is to be able to identify hazards. Okay, so we want to identify hazards and get them listed out for a piece of design work or a project. And the point about hazard identification is that there are many tools, practices, and techniques for hazard identification, and one of the arts of safe design is to select the appropriate tools, practices, and techniques for hazard identification appropriate to the scope, scale, and complexity of the design work at hand. Okay, so step 1 is identify hazards, and we want to do that during design, of course. So during design, identify hazards that will exist with the design as it passes through its life cycle phases. Step 2, for each hazard, apply the hierarchy of controls and determine which which hazard controls are possible. And then step 3 is to determine which hazard controls are reasonably practicable to implement and implement them. And step 4 is to maintain records of the decisions to fulfill due diligence and duty of care requirements. And that process outline can be found in the Code of Practice, Safe Work Australia's Code of Practice, Safe Design of Structures, which is also mandated in some states and territories. So, yeah, I think that's the my answer to the question.
Thank you, Mike, for that. Over to you, Nancy. We've had a question that's come in again from Queensland, from Stephen. Good afternoon to you. Asking Nancy, do you see STPA replacing or complementing other safety analysis techniques? Thanks, Nancy.
Well, the results of the other safety analysis techniques are a subset of what you get out of STPA. So any time you're spending on the others is a waste of time, frankly, and they're too late. They come at a time when it's too expensive to make any changes. You maybe you can add some redundancy or add some stuff that adds weight and cost and all kinds of and affects impacts performance. But what you really want to do is start this very early in the process. After you've got it designed in, and you do the analysis as you're designing, and you find out, you analyze each decision as you're making it, there's really no reason to do any analysis at the end. So, but I do understand that this is new. It's different than what people are doing now. And so people are a little nervous about giving up what they're used to and what they understand and know how to do. So we find that people tend to do everything at first, and then they realize they don't have to, and they're spending way too much money doing the other techniques, and they tend to drop them and just use STPA.
Thanks, Nancy. And just to stay with you, and then maybe open this question up to Mike, because it's a really great question that's come in from Brett, who's in Western Australia. Brett is asking, how can we apply systems theory and safety management as practiced in hazardous industries to road safety? Nancy, do you want to kick off with that one?
Well, I did mention something. I showed a model that included a lot during my talk, a lot of aspects of road safety. What you have to do is just expand. STPA will work on it. You just have to expand the boundary of the system that you're looking at. You can look just at the car and some technical components, but you can look at the larger social system, rules, laws, procedures. All of those things on the roads can be handled using this kind of approach.
Mike, do you want to jump in and talk to that too?
Yeah, I just wanted to add that there's the Safe Systems Assessment Framework for Road Design, which is available from Austroads, and that's had a lot of research in its basis from universities in, I believe, in Adelaide, I shouldn't say Adelaide, in South Australia and Victoria, at least, if not wider than that. And the Safe Systems Assessment Framework really does put a systems approach on road design, which encompasses some of the principles of systems engineering and building safety in, the sort of thing that Nancy's talking about. So I strongly recommend people having a look at that.
Thanks, Mike.
I can't just add one word, is Norway's doing a lot of this now. They're looking at the whole road safety system from a systems thinking type of approach, and it's been very successful for them.
Thank you for that. And Mike, we've had a really interesting question that's come in from Wolfgang, who's in Queensland, asking, how do we calibrate personal risk setting to move it into the business context? Chess players versus skydivers. Thanks, Wolfgang.
Chess players versus skydivers, I like that. Have I done both? Yes. The main calibration tool in Australia, as far as I'm concerned, is the government's published value of statistical life and value of statistical life year. And those figures have been published since December 2014, so 7.5 years now. And the figures have been revised, are revised continuously according to CPI. But that is, from my perspective, that is how we achieve calibration. And it's not only how we achieve calibration, but we achieve calibration nationally with those figures published by the government. So yes, that is my answer.
Thanks for that, Mike. And just staying with you for the next question, was coming from Robert, who's asking you, Mike, to what degree complying with the Australian standards, to what degree does that secures the engineering design is safe? Thanks, Robert.
Yeah, it's a very common question on safety and design discussions and courses. So, for example, I'm an electrical engineer by background, so I'll pick on AS3000, for example. So there's no way that I would choose to deliberately contravene AS3000 for that's the standard for electrical installations, because to comply with AS3000 means to create an installation that is indeed safe so far as is reasonably practicable. However, there are some situations in which you have to deviate from standards. For example, in installing equipment in particularly difficult areas to access. And what you have to do is demonstrate that even though you're going against the standard, by working from first principles, your design is still safe so far as is reasonably practicable. So, and I think the other thing is to think about standards as an absolute minimum set of requirements. And I think that is really helpful to recognize that a standard is a minimum set of requirements, and whatever the standard is, let's comply with the standard, because that's good practice. It's based on lessons learned from the past. So we're going to comply with the standard, but then we're also going to think about what are the hazards associated with the design. What can we do about the hazards to make it safer so far as is reasonably practicable? And if that means going above and beyond the standard, then the law requires us to do so, so long as it is indeed reasonably practicable to do so. So yeah, I think that's my answer.
Thanks, Mike. We've had a question that's come in from Callum in Victoria, and to both of you, but we might open this up to you, Nancy, first. Callum is asking, what is the panel's view on how safety analysis and assurance activities can be practically integrated into design processes? And Callum goes on to say, and to what extent does the panel think integration of safety analysis and assurance into design processes is desirable? Nancy, do you want to start with that one?
Well, I think I've talked about it, and I just said something else about it. Of course, it's desirable. I mean, I can't imagine doing anything else. The alternative is that you spend a lot of money and time building a system. You do safety analysis on your design, detailed design. You find all the problems, and either you have to throw that away and start again, which never happens, or you're sort of stuck with what you've got. So you try and fix it a little bit, and then you put all these operational controls, which are very difficult to satisfy. Is it practical? Absolutely. I mean, that's all we're doing now in my group, and we do a lot of safety analysis, and most of the people using Stpa now are doing that. Are integrating it into the design processes. I should say, by the way, there's a lot of talk about reasonably, reasonably practical. You know, I know that this is the approach in the UK and in the Commonwealth countries. The US doesn't do that. Our standards don't talk about reasonably practical at all. We have a different kind of approach to regulation.
That's so interesting, Nance. Yeah, it's so interesting. And Mike, do you want to just extend your thinking on that one?
Sorry, I was on mute. Yeah, Nancy's just thrown me by saying that the concept of reasonable practicability isn't considered in the US. So I'm just thinking about what that means. But the question was, can you practically integrate the steps of safety throughout design? I think that was the question. And I would say, of course you can. And of course, it's not only practical, but it's required. And is it desirable? Well, I think it's required by law. So it's not just something that you need to consider doing. It's something that you have to do. And good, I totally agree with Nancy that good safety in design, good safety in engineering, it starts at the beginning and it carries on all the way throughout. You don't sort of bolt it on halfway through or at the end or something like that. No matter which tool, practice, or technique you're using, you need to consider it throughout. I think that's the answer. My answer.
Thanks, Mike. I just want to stay with you because we've had a question that's come in from Ashamal, who's in Western Australia, asking what are the principles for cost-benefit analysis when mitigating risk? And the example is risk reduction versus dollars spent. Thanks, Mike.
So the principle for cost-benefit analysis is really laid out in WHS and OH&S legislation. The legislation says we have to consider and weigh up the cost of hazard controls against the likelihood that a hazard can become harm and the severity of the harm that might result. And we can put numerical values on these. And we also have to apply a disproportionality factor in favour of safety, because the law is not concerned with what is disproportionate to expenditure. It is concerned with what is grossly disproportionate expenditure. So the framework for cost-benefit analysis really is outlined in the legislation in Section 18 of the WHS Act, and I think it's Section 20(2) of the OHS legislation in Victoria. I think that's my answer to that question.
Thanks, Mike. And we've had a question for Nancy that's coming from Michelle. Michelle is watching from New South Wales. Good afternoon to you. Nancy, Michelle's interested on your thoughts on the high reliability organisations and the effects of HROs and operational discipline on safety. Thanks, Nancy.
When I answer, I'm not sure that you'll be so interested in my thoughts. I think that high reliability organization theory is simplistic and naive and very dangerous. Many of the principles are either simplistic, as I say, or they're just wrong. I've been involved in a lot of major accident investigations in the United States. And surprisingly, large number of the worst ones had people who were following high reliability organization theory, and actually that caused the accident. One of which was, you all know, Deepwater Horizon, the Macondo accident in the Gulf of Mexico. BP had a vice president in charge of HRO. His whole job was to ensure that everybody followed HRO, and they followed every tenet of this thing. They had the worst accident record in the whole industry and always have. It 8 times worse than the next person in oil and gas production. I think it's dangerous and naive.
Thanks, Nancy. Thank you for that. And Mike, we've got a question that's come in from Carol, who's in South Australia, asking what is an applicable framework for safety for an engineering asset? Mike.
Yep. A good framework for safety for an engineering asset is the SafeWork Australia's Code of Practice Safe Design of Structures. And it's an excellent textbook on safety and design. And when I read the Code of Practice Safe Design of Structures, in my mind, I replace the word structures with what I'm doing. So I think it's a good code of practice for the safe design of whatever you're doing. Okay, but and it would be great if it was reissued, called the Code of Practice Safe Design of Anything. There is also in Victoria, there's a compliance code which is a code of practice for the safe design of plant, and that also provides an excellent framework for safe design. So I think both of those documents are really good frameworks.
Thank you, Mike. And Mike, we might just stay with you because we've had a really interesting question that's talking about the role of people in all of this. And this has come in from Joe. Good afternoon to you. Mike, in general, it seems that you need to understand risks to analyse them. What are the requirements on people who do these sorts of assessments? Thanks, Mike.
What are the requirements of people who do these sorts of assessments? I suppose I've got a couple of views on this. The first view I've got is I'm an engineer, and I cut my teeth in engineering and went through my apprenticeship and went through my various levels of engineering. And as I went, I had to learn about risk assessment. I had to learn about risk. I had to learn about hazards, and I had to learn about the various tools, practices, and techniques available for identifying hazards, analysing hazards, and then addressing them in design. And I guess my expectation is that, therefore, that all designers and engineers have a role to play in risk identification, hazard identification, hazard mitigation, risk mitigation. So I don't think necessarily that there's some special person with a special set of skills that is always required. My second thought is that there are very definitely safety engineers. You know, people like Nancy is an extreme example, of course, of someone in that mold. And safety engineers practice the art of safety in engineering and safety in design, and are, of course, very good people to be able to consult and advise on the tools, practices, and techniques to make things for engineered safety. So I think that answers the question.
Yeah, I think it does. And Mike, I just want to stick with you on this particular theme. And we've had a great question that's come in from Anthony in Victoria, asking, what can we do when senior managers don't make adequate resources available for safety mitigation? Thanks, Mike.
Yeah, sure. This is, again, a common question that comes up in the likes of safety and design training. And the point is that when a senior manager makes a decision that adversely affects safe outcomes, they are actually taking on the duties of designers themselves, and they're making a decision that affects design outcomes, and therefore taking on duties of designers. My recommendation to anyone who has a senior manager who says, no, you're not having as much time or as much money as you need to make something safe so far as is reasonably practicable, is firstly, you need to challenge it. You've got to be brave enough to challenge it if you really think you need more time or money or that sort of thing. And secondly, at the end of the day, keep records, because if something goes wrong and the root cause of something going wrong is that senior manager's decision, then it needs to be very clear who made the decision. So record keeping becomes really important in those circumstances.
Thanks for that, Mike. We have quite a few questions in that mode, and we might come back to that if we have time. Nancy, we've had a question come in from Subraj, who's in New South Wales here, asking, is there feedback to respond to a problem given new operational information that design has not considered? New issues emerge in an operational environment that may be different from design calculations, assumptions, or testing simulations. So how do we deal with that, Nancy?
Well, I think the problem is actually more than just that the design didn't consider. The bigger problem is that the world changes. People change their behavior in systems, the environment changes, companies change, and they should change because that's the only way they can exist and thrive. So there's always going to be change. And the problem, and so I've come up with something I call assumption-based leading indicators. And basically, the safety analysis has been based on some types of assumptions about the operational environment and how this is going to be used. And so what you want to do is during operations, check those assumptions to see if they've changed, because if they've changed, that means you're migrating to states of higher risk and that you could have a problem. We've tried this. This is a relatively new paper that I wrote, but we've tried this on a major international, very large major international airline, and it worked like a charm. So we're still doing some more on it, and it can be done.
Thanks for that, Nancy. Mike, we've had a question that's come in from Johan in the ACT, asking that Johan is working as a subcontractor, asking how to ensure that client decisions don't adversely impact the safety of our vertical transportation systems. Thanks, Mike.
I'd like to, I don't know about vertical transportation systems, I presume that means lifts, but clients impacting safety is a real issue and it's a problem. And the way, I don't know if there's a way to address it, but the way I approach it is that if a client is making a decision that affects, it's the same as if a senior manager is making a decision that adversely affects safety. If a client is making a decision that adversely affects safety or means that the design is not safe so far as is reasonably practicable, then the client needs to take responsibility for that. And it's really important to have really clear, open channels of communication with the client, so that if the client fires in an instruction, you must do this, and that is bad for safety, that there is an open communication back to the client to say, hey, that's not safe so far as is reasonably practicable. We can demonstrate it's not safe so far as is reasonably practicable. And do you realize that when by issuing that instruction, that you as the client is taking on the duty of designer at that point, the legal duty of designer, and that if something goes wrong, the responsibility will come back to you as the client. So I think clear and open communication channels are essential in this regard. Absolutely essential, and clear delineation of responsibilities. And this is where good safety planning is so important, that you identify not only how you're going to make your design safe so far as it's reasonably practicable, but also you're going to identify who's responsible for what and what are the channels of communication throughout the design that works. So it's not all done in isolations or silo.
Thank you, Mike. And time is marching on as always, but Nancy, we've got a question to you. You did cover this off in your presentation. It's coming from Arthur, and Arthur's in South Australia, saying it appears, as you confirmed, that STAMP and Stpa is best planned at early stages of a project. But is it simple to apply at any stage? Thanks, Nancy.
Well, really quick answer to that, yes. It's simple. It can be applied anytime, and people are doing it anytime. It works the same way, whether you do it early or late.
Thanks. Thank you for that. And staying with you, Nancy, Clinton in Victoria has asked, what companies are using these engineering system management tools? What type of companies? Thanks, Nancy.
Well, I can't tell you what companies. I mean, I could list them, but there's thousands of them now. We have a workshop yearly. We have over 2,000 people that attend, and hundreds of companies are attending and using this. For example, in just an automotive, maybe 150, 160 different companies attend. So I can't tell you all the names. I could list some of them, but we haven't got enough time. would take several hours for me to start listing all the ones that I know about. And I'm always surprised. People send me mail. By the way, I'm happy to answer mail if you're interested in some questions we don't get to here, but it's very widely used. I'm sort of amazed myself every time I hear about people, where they're using it and what they're using it for.
Thank you, Nancy. And an interesting question to put to you that is coming, asking, can Stpa be applied to systems that use AI to make decisions? An example being self-driving cars, where there's uncertainty around how the AI will behave in all situations. It's a pretty cool question.
Was that for me?
Yes, that one was for you, if you want to take it.
So I missed it. Can you repeat it?
The question that's been asked is that, yeah, can Stpa be applied to systems that use artificial intelligence to make decisions? An example is self-driving cars, where there's uncertainty on how AI will behave. Yeah.
I mean, it's difficult. It's difficult to do any safety analysis on a system when you don't know what it's going to do, and you can't prove what it's going to do. It could do any old thing. That's a difficult problem. I have a PhD student who's working on a dissertation on this right now. I tried to discourage him, but he insisted, and he thinks he knows how to fix this and that we can do something about it. He's starting to convince me, but it is a lot of this is hype. I mean, if we didn't call it smart software, these aren't intelligent. It far from intelligent. And we go through these periods when everybody starts using AI on everything, and then they find that there are really better ways to solve the problem. So I'm not convinced that this is something that's going to last for a while, but we're working on it.
Thanks. Mike, do you have any comments?
Amanda, I see one question there that I really would like to answer. Will your book safe wherever be released? And so before we run out of time, let me say I've rewritten the whole thing. It was just taken out of print because it's 25 years old and it's just too old. So I've totally rewritten it. It's called An Introduction to System Safety Engineering. It's a textbook. It has questions. It's written as a textbook. I signed a contract with the publisher. It will be released probably this fall. But if anyone wants an earlier draft, send me mail and I'll send you a draft.
Thanks, Nancy. Thank you for picking that up as well. Mike, there is a question that's come in around the D&C contractors having little interest for SID outside the immediate concerns of installation and may offer solutions different from intent, asking what regulatory controls are there on that. And that came in from Rebecca. Thank you, Rebecca.
Yeah, sure. The requirement of the law is very clear that designers, so D&C contractors, that's design and construct, so they're responsible for design. The designer is responsible for safety of the whole of the life of the asset, not only safety during construction, which obviously a D&C contractor is interested in construction, but the designer portion of it, they have to consider hazards throughout the whole of life of the asset or products being constructed or installed or assembled. And what regulatory framework exists? It's called the WHS Act, OHS Act, and regulations that really dictate that the duties of designer is to think about the whole life cycle of the asset.
Thanks, Mike. And just to finish, Chris is asking you, Mike, if you are using Stpa. Are you?
That's a great question. Am I using STPA? The answer is no. I've been following Nancy's work for some years on STAMP and STPA, and I'm not using it. I'm only not using it because generally, what I'm finding in my work and my training is that we're starting from a lot more of a basic baseline and building up the concept of safety, safe design throughout the design and engineering lifecycle, and starting with fundamentally simpler processes. And at some point, we probably need to transition to STPA, is what I'm thinking.
Thanks, Mike. And as always, we have run out of time, but I just want to close. I mean, we had almost 2,000 registrations for this event, so it shows that a lot of people are interested and passionate. So I'd like to just ask you both, just very, very quickly, just Nancy and Mike, just a few words as to what you think is critical going forward, and advice you have to our audience who are clearly so interested in this field. Nancy, starting with you.
Well, I think we have to get away from understand the systems today are very different than they used to be, and we need to use new tools, new techniques, new approaches for them, because otherwise we're just not going to be very successful with them. That's it.
Thanks. Mike, bring us home.
My favourite piece of work with engineered safety is planning. And at the front end of a piece of work or a project or a design task is to plan safety work, and whether that would be following, for example, something like Nancy's work, STPA, STAMP, that sort of thing, or whether it will be following other techniques. I think having a plan is the best way of recognizing what you're going to do and gaining confidence in how you're going to make your design safe so far as is reasonably practicable. And then you can follow the plan and socialize the plan and gain confidence in what you're doing.
Thanks, Mike. So please join me once again in thanking Professor Nancy Leveson and Mike Hurd for their time and insights today. I'd also like to thank Engineers Australia's industry partner, Engineering Systems Management, for their support. If you have a couple of minutes, could you please complete a short feedback form which is linked in the description box below to help us improve and plan future sessions. Thank you again for joining us, and we hope to see you at our next Thought Leaders event. Thank you and good afternoon.